Welcome to the fascinating world of quantum physics. Today we'll explore the differences between classical physics and quantum physics, and how they shape our understanding of the universe. Classical physics can explain many of the events around us with remarkable accuracy. For example, if you hit a ball with a bat, classical physics can precisely predict where the ball will go and how it will behave. However, when it comes to explaining the behavior of matter at the subatomic level, the tiny scale of particles like electrons and photons, classical physics fails. In such cases, the most successful and logically consistent scientific theory we have today is quantum physics. Using quantum physics, we have developed many modern technologies. One core principle of quantum physics is that some areas exhibit high wave intensity, while others show low intensity, and some areas show no intensity at all. This behavior can be explained using the double slit experiment. When a wave passes through two slits, it splits into two waves. These two waves can interfere with each other, meaning they can either combine to form a stronger wave, which we call constructive interference, or cancel each other out, known as destructive interference. As a result, the pattern formed on the screen shows alternating bright and dark bands, known as an interference pattern. This pattern can be visualized using a wave diagram, where higher amplitude or greater intensity corresponds to brighter areas, and lower amplitude corresponds to darker areas. In 1801, British scientist Thomas Young first conducted the double slit experiment using light. He observed an interference pattern proving that light behaves like a wave. For the entire 19th century, scientists were convinced that light was purely a wave. However, this certainty was disrupted in 1887 when German physicist Heinrich Hertz observed the photoelectric effect. Normally, light shining on a metal surface does not cause electrons to be ejected. But Hertz discovered that light of sufficiently high energy could indeed eject electrons from the metal surface. If light were purely a wave, this shouldn't happen, yet it did, creating a major scientific puzzle. It was Albert Einstein who resolved this mystery. Einstein proposed that light is not merely a continuous wave, but instead, it is made up of packets of energy, called photons. Each photon's energy is directly proportional to the frequency of the light wave, expressed as E equals hf, where E is the energy of the photon, h is Planck's constant, and f is the frequency of the light. This means higher frequency light carries more energy per photon. For example, ultraviolet light, which has a higher frequency, has more energetic photons than visible light. This discovery earned Einstein the Nobel Prize in Physics. Einstein also explained that if light were purely a wave, a single photon should create a single spot on the detector screen. However, when many photons pass through a double slit, they collectively produce an interference pattern. This showed that individual photons behave like particles, but a collection of photons behaves like a wave. This dual behavior, where light behaves both as a particle and a wave, was incredibly surprising. Later, the double slit experiment was repeated with electrons. The results were astonishing. Electrons, like photons, produced an interference pattern, indicating that electrons also exhibit wave-particle duality. However, something even stranger happened. When scientists placed a detector to observe which slit the electron passed through, the interference pattern disappeared. Instead, the electrons behaved like particles rather than waves. This demonstrated that the act of measurement itself changes the behavior of quantum particles, a concept central to quantum mechanics. This phenomenon highlights that an electron's position is not fixed until it is observed. Instead, the electron exists in a superposition of all possible positions, and observing it causes it to collapse into a single location. Before observation, the electron exists everywhere at once in a probabilistic wave-like state. This led to the development of the wave function in quantum mechanics, a mathematical function that describes the probability of finding a particle at a given location. The greater the amplitude of the wave function at a point, the greater the probability of finding the electron there. This concept is known as Heisenberg's uncertainty principle, which states that it is impossible to know both the exact position and momentum of a particle at the same time. In other words, in the quantum world, you cannot definitively say where an electron is, you can only say where it is likely to be found. The next remarkable phenomenon in quantum mechanics is quantum entanglement. If two particles become entangled, meaning they interact and become linked, they remain connected even if separated by vast distances. Measuring the state of one entangled particle instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. Imagine flipping a pair of entangled coins. One coin stays on Earth while the other is sent to Mars. The moment you check the Earth coin and see its heads, you will instantly know the Mars coin must be tails. This happens instantly, faster than the speed of light. Scientists are still trying to fully understand how this communication works. The strange properties of entangled particles form the basis for quantum computing, which exploits superposition and entanglement to process information in ways that classical computers cannot. Another fascinating quantum phenomenon is quantum tunneling. This allows particles to pass through barriers that would be impossible to cross under classical physics. If an electron wave encounters a wall, part of the wave can penetrate and pass through the wall, meaning there's always a small probability that the electron will appear on the other side. This tunneling is not just theoretical, it's crucial to processes like nuclear fusion in the sun, and also enables technologies like semiconductors in modern electronics. The likelihood of quantum tunneling depends on factors like the height and thickness of the barrier, and the mass of the particle. Quantum tunneling might sound like science fiction, but it's a real and essential feature of our universe. These mysterious and fascinating properties, uncertainty, entanglement, superposition, and tunneling, are why quantum physics is so essential to understanding the subatomic world. This concludes today's presentation on quantum physics. We hope this provided you with a clear overview. If you enjoyed this, you can subscribe to the YouTube channel Science Sphere for more videos like